like all the video playlists and stuff. Okay, so everyone knows what a baseball diamond is. A baseball diamond is a square of side length 90 feet. So everyone knows what that is. And you know how the first, it goes home plate, first base, second base, third base in anti-clockwise order. So everyone knows that. All right. So baseball. Player, oops. Okay. All righty. Player A runs from home plate to first base at a speed of 20 feet per second. How fast is the player's distance from second base changing when he is halfway to first base? And everyone knows that here's a baseball diamond. Does it let me? No, it doesn't. That's hold on. I need to get this right or else it's gonna bother me. Okay, there we go. All right, so baseball diamond, it's a square. Each side is 90 feet, right? And home plate is over here, first base, second base, third base. All right, and the idea is that you start from home plate, you run to first base, then you run to second base, then to third base, and then back home. All right. I mean, I assume everyone kind of knows the basics, but so how do we do this problem? How did you know 90 feet? Because I told you in the problem. All baseball diamonds are 90 feet between the bases. Okay, so how do we start this problem? Label what we are looking for and what is given. Okay. So let's copy this again. Let's remove all the markings. Okay, so, and then write out our givens in once. Okay, so we'll write out our given information, and then we also have our equations, right? So I have a diagram, I have information, and I have equations. So let's start filling all this in. So can someone kind of tell me how to fill everything in? You can give me any part of this. You can give me some of the given information. You can give me some of the equations. You can tell me how to label this diagram, anything you want. But remember, if you tell me something like x equals something, you have to also tell me what x is supposed to be. You know, each side is 90. Okay. Now, each side is always 90, so each side is a constant 90. Alrighty. dx dt equals speed. I don't know what x is, and I don't know what speed you're referring to. dx dt equals speed is not a mathematical equation, and I don't know what x means. dx dt equals 20. Again, I don't know what x is, so I can't say whether you're correct. I don't know what that means. I can't just write here dx dt equals 20. What is x supposed to be, right? Let's see what other people are saying now. X is one of the sides. You just told me each side is 90. So how can dx dt equals 20? Each side is 90. Those aren't changing. So X is not one of the sides. X is the rate. Well, if we're going by what Damien said and dx dt is supposed to be 20, if dx dt is supposed to be 20 feet per second, then x itself is not a rate, right? Dx dt is the rate of change of x, but x itself is not a rate. X is position of player A, so can you be more specific? Because a position is not a number. A position might be coordinates or it might be some length or something like that. I mean, you're getting closer to what I might want to call X. The distance from player to base 2, 45 feet. Is the distance from okay, so okay. So Carter said X is the position of player A, and my question to Carter was, you need to be more specific about describing what the position is. Brandon then said the distance from player to base 2. If you're trying to say that X is the distance from player to base 2, then that is not correct because that distance is not changing at a rate of 20 feet per second. And Damien said 45 feet, but again, 45 feet is not anything that's changing. 45 feet is a certain length that is relevant to the problem, but that's not something that's changing over time. I mean, how do we approach these problems, right? We go sentence by sentence. So the first sentence says player A runs from home plate to first base. So he is running along this line here from home plate to first base. And it tells us that his run speed is 20 feet per second. Okay, so you need to think about what is changing at a rate of 20 feet per second, right? This is a rate of change, 20 feet per second. So something in this problem is changing at a rate of 20 feet per second. What is that thing? Is it an angle? Is it a length? Is it a volume? Is it an area? What type of object is changing? A length. Okay, so there's a certain length in this problem that is changing over time and it is changing at a rate of 20 feet per second. So can you now describe what that length is? And typically, how do we describe lengths? We describe lengths as the distance between here and here, right? So can you describe to me what that distance is that is changing at a rate of 20 feet per second?
Since the player A is running towards to first base and halfway to the first base, from that distance to the second base, that's what you're calculating.
Well, the distance from second base to halfway point, this is a constant length, right?
Okay.
So that's not changing over time.
That position from home base, the half base from home base, would that be X?
Okay, this is still not X because the distance
Oh,
from
okay.
home plate to the halfway point is fixed. That's 45 feet. But you are getting closer, right? We have to remember the distance from the player to home plate is changing over time, right? Because the player is moving from home plate to first base. So you need to put that player at an arbitrary position. So I'm going to say that this player is just arbitrarily some point along the baseline from home plate to first base. So this distance here, that is what I'm going to call X, the distance that the player has already run from home plate to first base. So that I will call X. And now we can say, aha, that distance is increasing at a rate of 20 feet per second. Right? Because what does it mean to say that his run speed is 20 feet per second? It means that his distance from home plate, right, wherever he happens to be along this baseline, this distance to home plate is increasing at a rate of 20 feet per second. Right? He might be over here, he might be over here, over here. He can be anywhere along this baseline, right? You don't know, right? It's changing over time, that position. Okay, now can you start to fill in the rest of the problem? So I've essentially done the hardest part, right? Starting it off for you and defining one of the two variables, or one of maybe the three variables, right? I've done now that first sentence. Player A runs from home plate to first base at a speed of 20 feet per second. I have now defined X to be the distance from home plate to the player, right? And I can now say that dx dt equals 20. Okay, so that first sentence is taken care of. Can you now get any other information from this problem? From X to second base is Y. Okay, so let's call that. So here's second base, and here's the player's position. So from second base to the player's position, we're going to call that distance Y. Okay? And why is that important? Is Y equals 100? Y does not equal 135 feet. First of all, Y can't equal 135 because Y is changing over time, right? As the player moves up, right, Y is going to be a different length, right? X and Y are both changing over time. Right? As this player moves up and down this baseline, right, this distance here changes. Again, don't guess about what these values are. Just look at the problem, right? I've already taken care of the first sentence. So now we're trying to take care of the second sentence. And Emily has already started off for us by defining a very useful variable, y. And that variable y is going to come into play when we parse out that second English sentence. I saw some people typing some things. Again, look at the sentence. How fast is the player's distance from second base changing when he is halfway to first base, right? That signals we have two pieces, the when and the question. Can you tell me that first part? So let's see what Emily says. Because you're trying to find rate of change of distance to second base from halfway to first, does the player have to run 135 more feet to second base? First of all, the player does not have to run 135 feet to second base. The player's position is changing. The player is not at 45 feet. Everyone needs to get that out of their head. The player is not at 45 feet, right? The player is at some arbitrary location along the baseline, and I just happen to want to know how fast something else is changing when he happens to be halfway to first base, right? But the player is not just standing there at 45 feet. Again, let's look at the sentence. The first part of the sentence, right? This is how we've done every single related rates problem in this class, right? We go sentence by sentence and try to translate the words into mathematical equations, right? How fast is the player's distance from second base changing, right? So that is telling you, that's the question. It's telling you exactly what you want to find out. So what do you want to find out in this problem? Let's see. So Damien says, is it how fast y is changing? So dy with respect to t. So dy dt. That's correct, right? How fast is the player's distance from second base changing? Well, the player's distance from second base, we've actually called that whole thing y, right? So that whole thing is just y. So this question is asking, how fast is y changing? So there you go. That's dy dt. So the question is asking you to find dy dt. Now we know that that's only going to be at a certain time, right? All these related rates questions are phrased as you want to know something when something else is true, right? So when he is halfway to first base, how would you describe that in mathematical equations? Ninety minus x is not an equation. 90 minus x is an expression. The Carter says when x equals 45. That's correct, right? Halfway to first base is equivalent to saying that x is equal to 45, right? So far, notice that what is happening here. This is just like any other related rates question, right? You have several quantities that are changing over time, but they kind of depend on each other, right? X and Y here depend on each other, right? Because we're going to see that there's an equation between them because if each base is only 90 feet long, obviously X and Y can't be arbitrary. We'll see that in a second. But the question is saying that X is changing over time and X itself is increasing at a rate of 20 feet per second. And you are interested in finding out how fast at what rate is this distance y changing when x happens to be 45, right? Y is changing over time, right? At some point y, whoops, erase this. At some point y is very, very long. When the player first starts running, y is very, very long. Actually, that's really gross. I'll just put it on here. When the player first starts running, the distance y is a very, very long distance. Then when the player starts to run a little bit more, that distance gets smaller. Then when the player is almost right at first base, that distance is pretty small, right? It's close to 90 feet. It's 90 plus a little bit, right? So that distance from the player to second base is changing over time. That is very important for everyone to understand. The player is not just sitting there at 45 feet. Okay, now let's put in the other constant. So this length here is 90. And what does that make this pink length? 90 minus x. Okay, so now can you come up with an equation that relates the two variables x and y, right? We no longer need to see the question because everything in the question has already been converted to mathematical equations. Right, that's this part over here. Can you now give me an equation that tells me something that is true about x and y no matter what time it is? So let's see. So Yingfei says 90 squared plus 90 minus x squared equals y squared. That's correct, right? I have a right triangle here. Now, what do we do in related rates? Once you have all this, so do I have all the given information? Yes, I went through each sentence in the problem and I translated it into words. Is this an equation that is true for all time? Is this true for all time? Yes, no matter where the player is along the baseline, this should always be true for x and y. Now what do I do? Once I have that equation that is always true for all time, what is my next step in a related rates question? How do I introduce dx dt and dy dt? I mean, somehow I have to introduce them into the problem. Right, find the derivative. So when I find this derivative, let's see, I get 2 times 90 minus x, right? The derivative of 90 squared is 0, so that derivative goes away. 2 times 90 minus x times negative dx dt by chain rule equals 2y times dy dt. Right, so I differentiated both sides. And now what we're going to do is all this information we are now going to substitute into the equations. Okay, so I get equation 1 star and equation 2 star. So I need to put in x equals 45. So I get 90 squared plus 45 squared equals y squared. That's from the first equation. And I also need to put in dx dt equals 20 and x equals 45. So let's see. So here I get 2 times 45. So I get 90 times negative 20. So that's what? Negative 1800 equals 2y dy dt. Okay, good. So those are my equations now, right? These are true only at the time. True only at time when x equals 45. But now my goal is to solve for dy dt, right? Dy dt equals question mark. Well, from 1 star, we have that y is equal to the square root of 90 squared plus 45 squared. Right? If you really want to, you can just use a calculator, but you can also just say factor out 45 squared, and you get 2 squared plus 1. So that's 45 times root 5 if you really care. But it doesn't really matter. You can just leave it like that. And then substituting that into equation 2 star. So let's see, dividing by 2, I get negative 900, and I get dy dt equals negative 900 over this ugly square root, and that is in feet per second.